Hey everyone, what's going on? So we're going to be talking about chapter 12 here, which is gravity and gravitational potential, especially in the case of us not necessarily being on Earth. Along with this, I'm going to be going through some pertinent equations. So we'll dip into each of the topics covered in chapter 12 itself, or rather the ones that I think we really need to emphasize. And then I have some sample problems for us, and I have 4 of them ready. So just to forewarn you guys, if you guys had any for discussion this past week, or you who still have the notes for that, what I'm going to be doing for the pertinent equations aspect of this is going to be very, very similar. So if you want to skip to the problems, go ahead. So without further ado, though, let's get into our pertinent equations. So for Newton's laws of universal gravitation, now this is a very broad subject, or rather topic, and it covers a lot of different things, especially when we're talking about gravitation. So one of the main takeaways from this was that we found this equation where our force is going to be equal to G times our mass 1 times mass 2 divided by our radius squared. Now, there are a few things to note about this. This G is not our lowercase g, our 9.81 meters per second. That's not what this is saying. This G is our gravitational constant. So I'll say gravitational constant. And we have it that G is going to be equal to 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. Really strange units for this, but this just so happens to be what it is. So considering we have a mass 1 and mass 2, this is the force between the two of them, meaning that it's reciprocated. So if we have 2 objects like this, then we would be able to find that force just between the two of them in just both, how they're both being pulled towards each other. And the last little part about this R is not just a radius. This is the separation between both of the bodies. So we could say this, to their centers of mass, which is a very important note, that will be their R, their separation from each other. So we'll say this, separation from M1 and M2. So a few other things in this were that we talked about the inverse square dependence. So what this is saying is more of a conceptual aspect, where it kind of leads into some of the equations that we have, especially that of how we find our 9.81, which I'll talk about in just a moment. But we have it that our lowercase g will either increase or decrease at a proportionality of 1 over r squared. So the actual equation for this, to find g within itself, is going to be equal to our gravitational constant times whatever the mass is that we're considering as our gravity or gravitational attraction. This mass could be the mass of Earth, the mass of the moon, the mass of the sun, anything along those lines. And then we're going to divide that by the radius of that object, or rather the distance that we're considering it from, squared. And I kind of want to highlight why I said wherever we're considering it from, because if we say that this is the Earth, well, we know that it's going to have some radius. Let's call it r sub e. But this is really only for any object that is on the surface of it. What if we wanted to talk about, let's say, a satellite that's orbiting Earth? Well, if this satellite has some other distance, let's call it r of s for the distance for our satellite, then we can describe the gravity on the actual satellite as g times the mass of the Earth divided by radius of our Earth plus that separation of the satellite. Now, the reason I'm not putting the mass of the object here is because in situations where the mass of the Earth is much, much, much greater, or not even just mass of the Earth, but whatever that other object is, if it's much greater than the mass that we are considering, in this case, our mass of our satellite, we're going to find that the gravitational attraction towards the mass of the satellite is nearly negligible compared to that of the mass of Earth. So if we're dealing with situations where we're at some height above Earth, then this is the kind of situation that you want to be using. So the next part I really want to get into are Kepler's laws. So Kepler's laws there are really three of them. So I'll say that the first and second one kind of go hand in hand, but the third one is describing the equation. So without getting too wordy on this and writing it out specifically, I'll just say what they are. So the first of Kepler's laws states that the orbits of a planet are ellipses with the sun at one focus. So what does this mean? So I think it's better to kind of draw this to see. So, oh, that's not an ellipse. So we'll say it's kind of like this. You guys get the idea. So what we can say is that this sun will sit somewhere within this right here, where it'll kind of have like some focal point. But the second one ties almost directly into it. And what it states is that planets sweep out equal areas in equal times. So while the first one described the path and location of the sun, this one kind of describes the behavior along the path. So what this says exactly is that if we consider two arcs, okay, where their center points are at the center of the sun, or rather their vertices are at the center of the sun, then we can say, if we consider this area, or rather this arc length A, and this arc length B, if the amount of time it takes to elapse in each of them is equal to each other, then we can say that the areas of those arcs are equal to each other as well. So we could say that the A of area will equal B area. And the third law says the period of a planet's orbit, T, is proportional to the 3/2 power of its average distance from the sun, R. So this is trying to put in words an equation. And I should just make this clear. I'll say 1 and 2 go to this. And then 3, we have that our period of an orbit is going to be equal to some constant times r to the 3/2. Well, what is that constant? That constant so happens to be 2 pi divided by the square root of g times the mass of whatever the sun is. I'm going to note it like that, and just know that this notation, this sun, or this right here, it's just equal to saying sun. This kind of goes with a lot of notation that you'd see if you continue astrophysics courses, or even astronomy courses for that matter. So you'll probably see something like this. Don't freak out about it. This won't be on your exam, but just know that this kind of notation exists. So we can say that since this is our constant, we're going to have to multiply again by our 3/2 power of our average distance from our sun. So that's really it for Kepler's laws right there, at least saying them explicitly. But now we kind of move on to gravitational potential. And while we defined it before, as U is equal to mgh, there's a stipulation here that kind of makes it impossible to solve in the aspect of space and planets and everything with the astronomical aspect to it, because we define here some point always where our potential is going to be equal to 0. How do you do that in a space that we've kind of thought is infinite? There's always going to be something there. So the way we'll now describe this in terms of attractions between planets, so we don't necessarily need that 0 point, at least in the way that we normally think about it. I'll note on that in a second. But the equation that we now have for it is our negative g times our m1, m2 divided by r, where this is still our separation between them. But now we are able to say, for the exact thing that we had here, the exact problem, we now have the stipulation that when our gravitational potential is equal to 0, we are at infinity. A 0 potential is an infinite distance away. So if we're considering an aspect of, let's say, three of these dots, let's say, and they have some gravitational influence around each other, then we see that we'll never hit a point, even if we're all the way up here, or we're all the way up on like my ceiling from that matter, we're still going to have some gravitational potential in the aspect of our system. So we can only say that if there is no other force in that region, or rather the farthest point we could possibly conceive, it's still past that. So keep that in mind with gravitational potential, is that essentially you don't need to solve for your gravitational potential at 0. It's just assumed to be at infinity. And then energy conservation. This is kind of something that's better in practice than it is just kind of trying to define equations, because we've already talked about the conservation of energy. And we know that it's going to be our kinetic energy initial plus our gravitational initial is going to be equal to our kinetic final plus our gravitational final. Rather, not our gravitational, but our potential. So, oh, I wrote that wrong. It should be an F. So this would just be a matter of plugging in how we exactly do it. So if we have a planet that's moving in a linear path, let's say, then we'd have something like our mass times our velocity squared plus, or rather minus, because now we have a negative sign in front of our potential. This would be negative g m1 m2 divided by the separation. And let's say this is m2. I don't know. Very, very problem specific, as you guys are aware. But this would be the general kind of substitution that you would want to go for. So yeah, that's really it on the pertinent equations for this chapter. While there are other things like escape velocity, I actually have problems on that where we'll just talk about that more, because those are highly specific cases. So yeah, let's get into it. So for problem 1, it says that we want to consider an asteroid with a radius of 19 kilometers and a mass of 3.35 times 10 to the 15th kilograms. This thing is massive. So what we want to do is assume that the asteroid is roughly spherical. So it'll kind of make our calculations a little bit easier. So what is the acceleration due to gravity on the surface of the asteroid? So we're going to find our little g here. And for this part B, we want to suppose that the asteroid spins about an axis through its center. So essentially a sphere rotating, like Earth, with a rotational period of t. So what is the smallest value the period can be before the asteroid starts to lose rocks on its equator and fly off? So let's draw this asteroid right here. Let's say it's roughly spherical. We have all these little crater marks. And we're going to say that from some, let's assume that this is our center point, all the way to the edge, we're going to have some distance r. Now, this r value is going to be equal to 19 kilometers, which is going to be equal to 19,000 meters. Our mass of the asteroid we're given, which is going to be 3.35 times 10 to the 15th kilograms. And while it may not even be pertinent in this equation, if we're saying that it's a sphere that's rotating about its axis, or rotating about its center, then we can say that our moment of inertia of our asteroid is approximately equal to that of a sphere. And that's going to be equal to 2/5 times the mass times our radius squared. While this may not play a part in this, this problem, sometimes writing these sort of things down, whether or not you're going to need to use them, will be helpful. So for part A, we want to find what is our acceleration due to gravity of our asteroid. So the equation that we have for this is our gravitational constant, and it's going to be our mass divided by our radius squared. And just writing on the subscripts of the asteroid, we'll say that this is our mass of our asteroid, and this is the radius of our asteroid. So this is kind of trivial at this point. Once you have this equation, you can just plug in your numbers. So this is going to be 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. The mass of our asteroid is 3.35 times 10 to the 15th kilograms. And we're going to divide that by the radius of it, which we know is going to be 19,000 meters squared. So then we get that the acceleration due to gravity on the asteroid is going to be equal to 6.1896 times 10 to the negative 4th meters per second squared. Compared to what we're used to, this is nothing. You'd essentially be in zero gravity right here. In terms of the regular 9.81 that we're used to. Now for very, very small objects, that's not necessarily going to be the case here. This is going to have enough of an attraction that things will be pulled towards it. And really going on with the rest of this chapter, if anything is small enough, it'll have an attraction. So for part B of this, though, oh, this is actually the answer. So I'll circle this. So for part B, it says, suppose the asteroid spins about an axis through its center like Earth with a rotational period t. What is the smallest value t you can have before you lose rocks? So with situations like this, what we're essentially trying to find is when our centripetal force on whatever object we're considering is going to equal the force of gravity of whatever object we are considering. So what we'll say here is we'll start to define some of those relationships prior. So knowing that we essentially want to get to the point of this, then why don't we define things like a rotational period or something like that. So we can say, since it's given to us that we want to essentially find our period, then we know that this is going to be equal to 2 pi over omega. Well, we don't have an omega, but we do have things that are going to be, we do have relationships that can find us omega. So our omega is going to be equal to V over R in an ideal sense. So this R is going to be the radius of our asteroid. So we get this is going to be V, and then we'll say this is R of our asteroid. So if we plug this in, we get that this is going to be 2 pi divided by our v over our r of asteroid. And then that just equals 2 pi times the radius of our asteroid divided by its velocity. So now we have an equation that relates our period to the velocity on the surface, or rather the perpendicular velocity, or the velocity that is going to be tangential to the rotation of the surface. So kind of going with this equation right here, our centripetal force is going to be mv over r. That's something that we know. Our force of our gravity is going to be mg, where now we're not going to be dealing with our 9.81. It's going to be this that we solved for in part A. So we get that it's going to be our mv squared over the r of our asteroid, and that's going to be equal to mg. Right now, we're just considering on the surface of the asteroid some object with some mg. So taking away this mass, then we get that our velocity is going to be equal to the square root of g times the r of our asteroid. Making some substitutions into our period, we get that t is going to be equal to 2 pi times the r of our asteroid divided by the square root of g is the r of our asteroid. So at this point, we can start to plug in numbers because we have our period in terms of things that we already have, quantities we have already solved for or were given. So this comes out to be 2 pi times 19,000 meters divided by the square root of what we had solved for beforehand, which is 6.1896 times 10 to the negative fourth meters per second squared times 19,000 meters. And by plugging this into the calculator, let me do this really quickly. We get that our period must be 3.481 times 10 to the fourth seconds. So if we want to put this in terms of hours, let's say, then we get that we would have to take that number, 3.481 times 10 to the fourth. And we're going to want to get hours. So there's 1 hour in 3,600 seconds. So we'll just divide that number by 3,600. And we get that it would take approximately 9.67 hours. Okay. So we're able to find our period in 2 different ways. The main takeaway from this one is know that if you want to talk about an object that is that is just going to fly off based on the period of rotation, then you need this condition to be true. This is not a y, this is a g. Just making that a little more clear. Okay, let's go on to the second problem. So question says that binary stars Centauri A and Centauri B are binary stars with a separation of 3.45 times 10 to the 12th meters and an orbital period of 2.52 times 10 to the 9th seconds. Assuming the 2 stars are equally massive, which is approximately the case, determine their mass. So the way this is going to look for us is if we draw this orbital path and we consider that this is Centauri B and this is Centauri A, and they'll have some angular velocity, omega, and they have some separation that we're given as essentially d, or we'll say 2r in this case. Well, that's going to be equal to 3.45 times 10 to the 12 meters. Additionally, it's good to note that in the center of this will be our center of mass, the point directly in the center of their circular orbit. Also, we have to assume that this is a circular orbit. So writing out some other pieces of information, we have our 2r is going to be equal to 3.45 times 10 to the 12 meters, meaning that our r value is going to be 1.725 times 10 to the 12 meters. Our period is given to us as 2.52 times 10 to the 9th seconds. And we're also given that the mass of A is equal to the mass of B, which we can just say is equal to our mass. And this is the quantity that we're going to want to solve for. So let's write out what the force of their attraction is. So we'll say that our f of g, uppercase G, is going to be G m1, m2 divided by their separation squared. So putting this in terms of our quantities that we know for this, instead of writing mass of A and mass of B, since we know that they're equal to each other, we can just say it's their mass squared because it's multiplying itself by itself. And then our separation happens to be 2r squared. So just writing this out a little bit more, we'll get that this is 4r squared. Okay. So another thing that we know about this system is if we're considering the orbit to be circular, then we're going to have some centripetal force, which we're going to say is mv squared over r. Where this is no longer our separation, this is just the distance from the center of mass. So to be able to find that mass, what we can do is equate the two of these. So we get that our force of gravity, or gravitational attraction rather, is going to equal our centripetal force. Putting this in terms of our quantities we already have, we have our gm squared divided by 4r squared is going to be equal to mv squared over r. And now we can just start doing some simplification. So our radius on this side, well, we can take that off and we no longer have an exponent for the radius in our gravitational attraction. Our mass also cancels, so we just go over the squared there. And what we're left with is a relationship that our velocity is going to be equal to the square root of gm over 4r. Okay. So a way that we'll be able to determine the mass is we're going to need to use our period to our advantage. So the equation for our period of a circular orbit is going to be 2 pi over omega. Now omega in this case is going to be v squared over r. So we get that 2 pi divided by v over r. Sorry, it's not going to be v squared over r. Omega is going to be equal to v over r. So this simplifies to 2 pi r over v. And we just solved for our velocity here. So we'll plug that in. So we get this is going to be equal to 2 pi times r over our square root of gm over 4r. Okay, let's take the reciprocal of this so that we're not dealing with a number divided by a number divided by a number. So by simplifying that a little bit more, get that it'll be 2 pi r times the square root of 4r divided by gm. Okay. Now, we could leave it as such. We could try putting the r inside of here to get them together, but let's just square everything to get rid of the square root. And we get is that this turns into t squared. It's going to be equal to 4 pi squared, r squared, and then 4r divided by gm. And since we want the mass all by itself, let's solve for m now. So we get that our mass is going to be equal to 16 pi squared, our radius cubed, divided by our period squared times g. And then plugging in numbers for everything, we get 16 pi squared, our radius, which is 1.725 times 10 to the 12 meters cubed, divided by 2.52 times 10 to the 9th seconds squared times our gravitational constant, which is 6.67 times 10 to the negative 11th newtons times meter squared over kilograms squared. And we get that the mass of each star is going to approximately be 1.91 times 10 to the 30th kilograms. So this is for each star. Or putting it lightly, these are massive. No, I'm just joking. Put it in terms of the mass of our sun and let's find out what that actual mass is. Yeah. Okay. So the mass of our sun is approximately 1.989 times 10 to the 30th kilograms. So both of these stars are actually pretty close to the size of our sun, if not just a little bit smaller based on the calculations that we have. So yeah, that's this problem. Let's get on to the next one. Okay. So Sputnik, the first artificial satellite to orbit the Earth, was Sputnik 1, and it launched October 4th, 1957. So the mass of Sputnik 1 was 83.5 kilograms, and its distances from the center of the Earth at apogee and pedigree were 7,330 kilometers and 6,610 kilometers, respectively. So what we want to do is find the difference in gravitational potential energy for Sputnik 1 as it moved from apogee to pedigree. Okay, so right off the bat, I want to describe what apogee and pedigree are to you guys. So remember what I was saying beforehand with Kepler's laws. So if we have the sun at focus, then there are really 2 points here that will hold a lot of information for us. One is the shortest separation from any part on the orbit to the sun, and the longest. So we're going to say that the shortest one is when we are at our distance at pedigree or perigee. And for the longest distance, it's going to be at apogee. So those distances we have are going to be 6,610 kilometers, which is equal to 6.61 times 10 to the 6th meters. And then our apogee is going to be 7,330 kilometers, which is going to be equal to 7.73 times 10 to the 6th meters. Additionally, it's pretty good to know this information about this. The mass of the Earth is 5.97 times 10 to the 24th kilograms. And the mass of our satellite, it is given to us in the problem that it's 83.5 kilograms. So we want to find the difference in gravitational potential for Sputnik 1 as it moved from the longest distance away to the shortest. So we have it that our gravitational potential at apogee is going to be negative g times the mass of the Earth times the mass of our satellite. And I want to make a good distinction here as well. This isn't the Earth, or sorry, this isn't the sun right here. This is us considering at Earth instead of the sun. The same principles would apply for perigee and apogee. So we're going to divide that by our separation at apogee. We'll do the same thing for perigee. So we get that this is going to be negative g times the mass of Earth times the mass of the satellite divided by that separation. So our change in our potential is going to be our final potential minus our initial potential. And it's saying that we're moving from apogee to our perigee. So we're going to say that this is u of p minus u of a. And making our substitutions, we get that this is negative g me times the mass of our satellite divided by that separation minus our negative g mass of Earth times the mass of our satellite divided by our separation. So we can pull out a lot of things here to make this calculation a lot simpler for us, or rather look nicer. So first thing we're going to do is take out everything in the numerators because they're identical. And I'm going to apply the negative sign here so that now we're, instead of having the negative of this number minus the negative of this number, we're just going to subtract this number as our larger one into this one because this will now have a negative sign. So we will say that our potential, or our change in our potential, is going to be g and e times the mass of our satellite times 1 over r of a minus 1 over r of p. And by plugging in numbers, for the sake of time, I'm not going to include units right here. And then by plugging it into a calculator, we get that it's negative 4.94 times 10 to the 8th joules. And this is something we would expect because you're going from your point that's farther away to a point that's closer. So you're losing that potential that you would have from being at a farther point to now a closer one. So having the negative sign here makes perfect sense. Please remember to do those sanity checks for yourself because it makes it so you can fix yourself on relatively simple conceptual things, such as why is there a negative sign there? So yeah, that's this one. And then for problem 4. So find the minimum kinetic energy needed for a 39,000 kilogram rocket to escape the moon. So this is where we get into kind of the concept of escape velocity, like I was talking about beforehand. So escape velocity, we'll call it V of E. It's the condition that our kinetic energy of what our escape velocity would have to be, the minimum of what it has to have is when we are equal to the attraction of the two objects to each other, or the moon to whatever object we are considering. In this case, the rocket. So we're going to find that the mass of the rocket actually gets canceled out here, but we'll go more into that in a second. Actually, we can do it right now. So substituting in some stuff, we get 1/2 mv squared. These are all equations that we know. But the gravitational potential here is going to be our g times the mass of our moon times the mass of the rocket again. We'll say this is the mass of the rocket. And then we're going to divide by the distance of wherever that rocket is. So we can say if we're already on the surface, what is that escape velocity it needs to have? So we'll say that this is just our r of moon. Okay. So the mass of the rocket cancels out. And what we're left with is that our escape velocity is going to be equal to the square root of 2 times g times, we'll just say this is m sub m divided by r sub m, where this m is just the moon. Okay, so the kinetic energy we're going to need to actually exit this, we're going to want to plug this right back in here. So what we get is that our kinetic energy for us to escape, we'll call it sub E, is going to be equal to 1/2 m times our escape velocity squared. So plugging it back in, you get 1/2 times the mass. And since we're squaring this number and there's a square root inside of it, we're just going to automatically apply that. So we get that this is going to be g times the mass of our moon divided by radius times the mass of our moon. Okay, so the 1/2 and the 2, they cancel. So we're left that the total kinetic energy, or the minimum kinetic energy required, would be the mass of our rocket times a gravitational constant times the mass of the moon divided by radius of our moon. And I want to make a note, just because I kind of remembered this. When I said that we're going to cancel out the mass of our rocket and that doesn't really matter, this is specifically for solving the above in terms of our escape velocity. Okay, so plugging in numbers now, get that this is going to be 3,000 or 39,000 kilograms times our gravitational constant, which is 6.67 times 10 to the negative 11th newtons times meter squared over kilogram squared. Mass of our moon, which is going to be 7.35 times 10 to the 22nd kilograms. And we're going to divide that all by radius, which is going to be 1.74 times 10 to the 6th meters. And we get that this whole kinetic energy turns out to be 1.1 times 10 to the 11th joules. Okay. We covered quite a bit here. So what I really want to get across to you guys is this stuff is just taking really, really similar concepts that we've dealt with before, such as conservation of energy, and just dealing, like you see, conservation of energy is huge for this chapter. So that centripetal motion and being able to take our rotational kinematics and kind of put them in such a way that we can translate them to these massive systems, literally the biggest ones we can conceive. So yeah, that's it. In the next video, I'll be talking about chapter 13, which is going to be pretty much my favorite topic of oscillations. So we'll get there then. Otherwise, I'll talk to all you guys later.